Broadcast is now starting. All attendees are in listen-only mode.
Well, it's 10 o'clock, so I guess we can start this presentation. Greetings, everyone. My name is Brian Chamberlain. I work for Carlisle Construction Materials, and I'm going to be talking to you today about roofing wind speeds, ASCE, uplift ratings, and warranties. A little about myself, though you can't see me. When I first started in this business, I had dark hair, fairly long, and I was single. And now I have 4 children that have all moved out, so we're empty nesters. My hair is gray, and I have lost some of it. So I've been in the business for a really long time, always on the technical side of things, trying to assist and work out the issues that are out there versus designs. And through that process, I ended up understanding a lot about ASCE and the code and those kind of things. In fact, I'm a member of SPRI, and which is the single ply roofing industry. And within that organization, they have a subcommittee that deals with code development. And so we work on that kind of language to help clean things up, make it a little bit easier for everybody to understand. And just a little bit more about myself. When I first started working the business, I started doing a lot of presentations. And through that process, I had a sort of a luggage bag that I'd always prepare for myself, so I could be on the road going. So it'd be pretty much the same as always. I got down to Florida one time. I had been wearing shorts down there because it's Florida. But then I had the day of the presentation. I was putting my clothes on, grabbed my pants, and they found out that it was my younger son's pair of pants. So they didn't fit at all. And so I had to wear basically shorts to the presentation. But that gives you an idea that we develop our specifications out there, and we start to always use the same things over and over again. And then we're not trying to keep up quickly with the things that have changed out there, such as the ASCE, such things as warranties. Those things are always in a fluid kind of motion, always being updated. The building code is always being adjusted. So trying to keep up with the specification and the change in the code can sometimes be a little daunting. So hopefully this presentation will give you some clues about some of the changes in the ASCE 7 and maybe even what to expect in the future. This is an AIA presentation, so it does have the accreditation necessary. These are the objectives today that we want to accomplish: learn the basic design process for choosing the correct roofing assembly, understand how roof assemblies are tested and rated for uplift pressures, review the changes within the latest versions of the ASCE 7, and realize the differences between warranty wind speeds and how they relate to all this stuff. Now, I know it's not lunchtime yet for most of us, so but I'd just like to show this off a little bit, and it's just a metaphor in a manner of speaking, because what we're trying to discuss here is the subject about the hot dog. And there's a lot of good stuff on this, pickles, tomatoes, onions, but you can't see the hot dog. And that's the whole purpose. We want to basically scrape a lot of the confusion that's off onto the subject, try to just distill it down to what we have to do to certify roofing systems to meet your local building code and to meet the criteria of the building. So we want to look at just the hot dog, nice, clean kind of thing. Because what we want to do is basically avoid problems that could happen out in the industry, such as what happened in this particular video. Now, this was in Cologne, Germany. And we have definitely, I'm sure that none of us want to be able to say that we were on national news because our roof blew off. So we want to avoid that as much as possible. So the whole purpose of the ASCE is to mitigate those kind of problems. Same as you see here with the hangar door. This was caused by a tornado. The wind got shoved into that side of that building, added additional pressures, and it just blew the roof directly off. So we want to avoid those kind of things, mitigate them, so we don't have those kind of problems. So we'll be talking about the ASCE 710, and then some of the changes that modified into the 716, and then we're going to actually introduce you to the ASCE 722 that was developed and started to be issued out. If you do any work in Florida, they are the first state to adopt this document at the end of this year. So they'll be using it also. Then we're going to take a little quick turn and check out the uplift testing to make sure that the assemblies are meeting or exceeding the pressures, and then we'll overlay that with warranties to see how they are dealt with and such. These are some standard inquiries we get in our office all the time. How does the International Building Code affect warranties, and how do the changes in the ASCE 7 affect roofing installations? And hopefully, you know, through this presentation, you'll have a much better handling of these kind of problems, and those questions will be answered. So this is the basic focus that we want to look at. The IBC, which is the wind performance, the ASCE 7, which is again wind performance, the FM 4470 and the ANSI FM 4474 testing, which is uplifting. And then we're going to look at wind speed warranties, which is wind coverage. Because again, what we want to do is basically avoid these kind of problems down here where you got the membrane just being completely peeled off or the roof system being damaged. Now, the first thing to be able to do the process properly is we need to know which document we're supposed to be using based upon the state you're in. There are, for instance, South Carolina is using the ASCE 7 edition of the 2016, while North Carolina is using the 2010. At this point, there's no state that has adopted the 2000 or is still using the 2005, but there are 7 states that do it differently. These 7 down here do it based upon municipalities, local regions, or those kind of things to make their decide what code they're using. For instance, in Illinois, they have 3 codes that they actually use. One for the state, one for the schools, and then there's actually the Chicago building code. So each one has their own kind of flavor on how they look at things. So you need to know exactly what documents you should be using to make sure you come up with the correct pressures. So that's one of the first things you need to research. This was actually listed off of the International Code Council website, and it's the latest one that they have for state adoption, January 2023. Now, within the building code, there's chapter 15, and within chapter 15, they define things like 1504 references adhered and mechanically fast systems, and the way we certify those systems is through a uplift testing, and then compare that with the pressures of the ASCE 7, and I'll get into that in much more detail. The ballasted systems cannot be tested associated to the ANSI FM 4474 test, because that's a test where the pressure is built up from underneath the membrane or the decking system, and then it starts to push on it. This is to simulate the negative pressure created by the wind blowing across. So that positive pressure is really considered to look at the negative pressure of the calculations. Now, the ballasted systems can't be tested because it's all loose laid, and it starts off with 10 pounds to 15 pounds per square foot of stone that you put on. Well, the test itself starts off at 30 pounds per square foot. So 30 pounds is much greater than 15, so all the stone just rolls off, so it fails by definition. So if you're interested in doing a ballasted system, you need to refer to the ANSI SPRI RP4 document, which I'm not going to get into today. We're going to sort of focus on the ASCE 7. But keep in mind that ballasted systems can be qualified and certified through the building code by following the ANSI SPRI RP4. Now, for the ASCE 7, doing the calculations, there are basically 5 factors that need to be used in the calculations. And the building height is one, because as the building height gets bigger, higher and higher, the wind gets stronger. Building's location, that's where we get the local wind speed off those maps. Exposure category, that's basically B, C, and D is urban, suburban, C is open terrain, and D is near large body of water. So these are all different factors, and that's an example there. And then openings, partial and enclosed. This is a partial opening building. And what that does is then you have different factors that you use in calculating the uplift pressures to compensate for those internal pressures that are brought in through those openings. And then there's the risk category. This is the steps by the ASCE to start to push towards more of a resiliency kind of design considerations. So they came up with these risk categories 1, 2, and 3, and 4. Prior to this, it was just building use importancy categories. So they've changed that a little bit to be more related to what we're dealing with. Risk categories are defined as such, where risk category 1 is low risk to human life. And those are just examples, again, agricultural type building or storage type establishment. I like to refer to them as being the golf cart shed that's over on a golf course. It's not that critical a structure, and so it can be fairly easily replaced. So it doesn't have a huge category to it. The most common one that we see is the risk category 2, which are used for commercial type buildings. And then risk category 3, 4. Those are the ones that we want to make sure that we have a good, robust system on it, or design versus the structure, because those are the ones that are going to store, have kids in for schools, public buildings, hospitals, power plants. These are the buildings that we want to make sure that can withstand a natural event. They are the infrastructure of our society, so we want to be able to get people to the hospitals that are working, those kind of things, so we don't end up having a problem. So those are one of the big things that people like to focus on, is making sure that they have their structures sound in that case. Now, in the ASCE 710, they introduced new maps from the previous ASCE 705. And what they did is they broke them down based upon the risk categories. They revised the calculations to be able to address that. They also redefined exposure D along the coastline areas, and they redefined the windborne debris region. And these are both incorporated in the IBC 2012 and 2015. And these changes involved exposure D, for instance. Originally ASCE 705, it was basically along hurricane coastlines. You could treat it as an exposure C versus an exposure D category. The reason that they had that was they felt that the waves that were created by the hurricane or storm that was coming in was sufficiently enough to create a ground roughness equivalent to an open terrain kind of condition. They did do some further research, and they decided to revert that back. So exposure D does have a higher factor associated to it because of the open condition across the bodies of water. Windborne debris region was actually reduced. They found through their studies that as a storm hits the coast, it does break up much quicker than they anticipated. So they have reduced those areas, but those involve special design considerations by the designer, such as making sure that you have proper window designs to withstand any kind of flying debris. In the ASCE 710, they also introduced the results to become ultimate. Originally, the results were allowable stress designs, and then they would add factors, the engineer would, to determine the structural needs of the building, dead loads, those kind of things, snow loads, and make sure that they're designed to be able to withstand those kind of loads along with it. The 710, they changed their attitude towards it, and they came up and said that, well, we're going to do the ultimate, because this was an engineering document, so they were trying to make it more easier for the engineer to do his calculations. So they decided to do ultimate. The problem is that roofing systems are not a structural component. They're considered cladding, and in that respect, they are allowed to just have to meet or exceed allowable stress design. And I've had people ask me, well, why is that? Why don't we use the ultimate anyway? And the basic reason is not my choice, but it basically the thought is by the engineers, they would prefer to have the roof system blow off than have the deck become a problem. So they don't want the cladding to be stronger than the actual decking or structural components. I know that in our industry, the legal ramifications of a roof having problems is actually much higher than most any other component on a building. So a lot of people feel it's necessary to make those systems very, very strong. So you can actually use whatever uplift pressures you want. I'm just giving you, again, the hot dog. You can basically, to meet the minimum building code criteria, you need to be able to reduce those pressures down to from ultimate to allowable. The way we do that is there's two methods. The first method is basically doing the calculations accordingly to the ASCE 710 or the 716 actually, and then you multiply it by 0.6. That takes the ultimate pressures down to allowable. The other way of doing it is converting the winds, because the wind maps that they have within the ASCE 7 are defined as being ultimate winds charts. So you can take those ultimate winds off those maps, and then you can actually convert them down to allowable. And once you have that, you can then calculate the uplift pressures with those winds, and then you'll have your allowable. It ends up being exactly the same by using either method. And this is allowed actually in the building code in 1609.3.1, where it gives us how to convert the winds from ultimate to allowable, and or the winds, excuse me. And so to get VASD, which is allowable stress design winds, you take the VULT, which is the ultimate winds, and you multiply it by the square root of 0.6, which is actually 0.775. Don't get this square root of 0.6 confused with the 0.6 that we use at the end of the math. It's not the same. So you can't do that. You can't take 0.6 and just multiply the wind. You have to actually do this square root of 6. This portion is not in the building code. I just added it to make it a little bit clearer, because a lot of people are confused what the square root of 0.6 might be actually. And so they also give us this chart or table 1609.3.1, where you can actually convert your wind. So if you're at 120 mile per hour zone based upon the ultimate, you can just look at the chart and see that it's 93 miles an hour, and that's where you would actually use in the calculations. This is the actual calculations themselves with all the definitions and everything, and I'm not gonna, this isn't a math class, but this is just giving you an idea of all the different factors that go in and how they're used. But this result up here, which is the main equation, is what's referred to as velocity pressure. And those velocity pressure is then used down in this formula, QZ. And what this has done, what we do with this is use the external pressure coefficient and an internal pressure coefficient to actually come up with the zonal pressures. This is where we get the zone 1, zone 2, and zone 3 is actually from this equation. And that's how we end up with the final for all those areas. Now, the wind maps, the ASCE 705 was a 100-year return period maps. And that's a mean return incident. And the ASCE 710 then modified that, and they basically came up with different risk categories and longer mean return incidents. For instance, category 1 is a 300-year, category 2 is a 700-year, and category 3, 4 is a 1,700-year mean return incident. While I was actually in a presentation with the ASCE 7 engineer who was introducing the 710, and there was a guy in the back who stood up and says, 1,700 years? We haven't been collecting that data for weather for 1,700 years. So how did you come up with that? Now, engineers are great people. I've got quite a few friends who are engineers. In fact, an engineer told me this joke about them. But he basically said they look at life a little differently than the rest of us. If there's a glass that's half full of water, a pessimist says it's half empty, an optimist says it's half full, an engineer says that the glass is two times too big for the amount of water. So they look at things a little bit differently. And so he was really happy when this guy asked that question, because the next 6 slides was basically a discussion on how they came up with 1,700 years, showing the math, the extrapolations, the charts, the graphs, all these things to basically come up with the final number of 1,700 years, which was great. The problem was that the guy stood up and says he was confused, but he just asked, from what I understand now, this is in the building code, and he said, yes, it is. So he said, that's all I need to know, thanks. So we have 1,700 years. Now, one thing to note is that the winds are not changing. The winds that are listed on the ASCE 705 are no different than what is listed in the 710. The difference is the mathematical adjustment of potential occurrence. Okay, so the winds have not gotten worse. It's just that they're looking at trying to make the buildings more robust to be able to withstand some conditions that may never occur. In fact, just to let you know what 1,700 year mean return incident means, is it's a 1 in 1,700 chance in 1 year of wind of this amount may happen, which is 0.00059. So it's the chances are fairly low that we'll ever see this type of wind. But if we design for it, then we won't have a problem with any kind of lower winds associated to it. At least that's the theory. Now, the 716, what they did here and introduce was a few other things. The nicest thing about it is they had the same number of chapters. They didn't change anything associated to it. By the way, the ones that we really focus on a lot is the analytical method for calculating, and we also look at components and cladding. Those are the 2 big chapters associated to roofing. The others can be used. There's a simplified method for that could be used, but it's a much more, I'd say, a little conservative in its approach. The analytical method seems to be much more accurate in what we're looking for. And then the components and cladding is obviously, since we're cladding, that's where we would fall under to make sure that we're installing it correctly. The things that they adjusted within the ASCE 716 from the 710, like I said, they changed the calculations. What they did is actually just add an elevation factor, and that's sea level elevation. That is not the elevation of the building. So it's how high is that above, where's the location above sea level? And I'll explain why they did that. They reduced the exposure B KZ factor, and I'll explain what that is for buildings less than 30 feet or less. They added a 4th. They broke up risk category 3 and 4, so now there's a map set for each one. And they added new roof zone areas for 60 feet or less building heights. And they also adjusted the GCPs, which is the external pressure coefficient, associated to 60 feet or less also. Now, this is the KZ factor, and this factor is used in the math, but you need to know what the exposure is for the building and also the building height. And this is just portion of the chart. This is 30 feet or less, and that's the portion that they changed originally in the ASCE 710 and previous. 30 feet or less for exposure B, which is urban suburban, was 0.7. Now they've actually added a gradation to it, and I think the reason they did that is to basically match up with C and D, which already had them included. So they were just sort of doing an editorial, but you can still use 0.7 if you want, but you can get a reduction in uplift pressures by going with a lower ones. The change here for elevation, they just added a KE factor, which is ground elevation factor. And the reason they did that, this factor here is a constant, but it is air pressure and or air density. And as we go higher and higher up, the air density actually gets less. I just recently watched the SpaceX, and it was even brought up as they were shooting the rocket up that the resistance for the rocket actually gets easier and easier as it gets higher and higher. So it's usually this ground area that we deal with the most that we have to like force things through. And so that's why the air density is much higher at a lower elevation. That factor is actually associated to Florida. So they want to basically adjust that factor, because if you're in Denver, you get a lower air density than you do. You have trouble breathing because you're not used to it. Athletics people go up there and actually work harder, get their lungs stronger. So when they come down to the higher density airs, that they actually supposedly have better physical strength than other people who don't go and practice in those areas. And this is the factor associated to that. And depending upon where your ground elevation is for the building, then you would get that reduction. There could be a reduction between 4% to 20%, but it doesn't start until you're at a sea level of 1,000 feet or higher. And this is the new wind maps. So 716 has a 3,000 year mean return incident map for risk category 4. And with 3,000 year mean return incident means there's a 1 in 3,000 chance in 1 year, which comes out to 0.00033. So getting even harder and harder to basically see these winds may actually happen, but that's what we do for the calculations to make sure we're reducing the risk. They did change the map, which made it a little bit more difficult to determine exactly what wind you may be using. But luckily, there are websites that you can use to help narrow and get better ideas on what your wind might be. Those two sites are the hazard.atcouncil.org and the ASCE7 hazardtool.online. This is an example of the ATC, and the nice thing about it is it gives you everything that you typically need for the 705, the 710, the 716. It also gives you the elevation. So we don't go over 1,000 feet here, so we don't use an adjustment on that, on the elevation factor, and you get all the risk categories. Now they do have these other mean return incidents on the chart. Those are actually used by engineers for different things. We basically, the roofing industry, and basically looks at the risk categories and these winds specifically in the calculations. So we don't use, these are all ultimate winds also, by the way. Now, the roof zones layout that we are so happy with up till the 710 was these 3 zones, zone 1, 2, and 3. Well, when you shift over to the 716, those are no longer used. What we use is this zonal map for zone 1 prime, zone 1, zone 2, and zone 3. Yes, they have 4 zones now, and one is zone 1 prime, which is a mathematical term. That is not a zone 1 foot, just to let you know. I've had people actually ask that question. So that's what we're going to be using for 716 and on. The way they came up with this is they went back to the original test they did in the 80s, which was a wind tunnel study on buildings and how wind basically moved and pressures were created. They had all these pressure taps. Well, they did the same study, but they added a significant amount more pressure tabs to be able to get a finer detail of how actually is happening up there on the negative pressures and to get it mapped out properly. This is a example of that study, and you have to imagine that the wind is being blown across here. So these are going to be the highest pressures, and then as it goes across, the pressures lighten up. And in this study, they found out that the corner is actually an L, and that's why they now have that L design in the configurations. And then we have our zone 2, which is the next higher pressure, and then they have the zone 1. But then they found out that it really lightened up in the center area, and that's where they found out that there was actually a zone 4 or zone 1 prime that they referred to it. And so that's why we have this kind of map now associated to it. And just to let you know, even though we have this L here, a lot of designers, consultants, and applicators simply just square that off. All the guys have been taught how to do the square for zone 3. So trying to figure out the L can be a little bit difficult and daunting. If it's a huge building, yes, they'll probably do it. But if you're standardized buildings, they probably just go ahead and square it off to make it easy for them. But this is what we use now is 0.6 times the height of the building, and the corners are legs widths are 0.2 times the height. The old formula of 0.4 times the height of the building or 0.1 times the shortest width is no longer used in the 716 and beyond. So keep that in mind that changes with the change of the document. This is the GCP pressures. I normally don't discuss this very much because it hasn't changed until the 716. It was always the same coefficients that they used, and these were where it was a 1, 1.8, and 2.8. And but when the 716 was introduced, they changed that. This is the charts that they have in the ASCE 7, and we can. Excuse me. And this is the same chart from the ASCE 716. And when you're looking at these areas, you're trying to figure out what are the coefficients that we need to use associated with these roof areas. You may have seen on structural drawings effective wind areas of 10, 20, 50, 100, so on and so forth. And people have always asked, which one are we supposed to be using associated to roofing? Well, that's actually the 10 feet, 10 square feet effective area. This was actually discussed in some industries, industrial organizations, and they came back and they said, yeah, 10 square feet is for roofing. So that's what we always focus on. And as we look at these lines come across, and when they hit the 10, that's when we scoot over and we'd be able to use those coefficients. For instance, if you look at 50, you'd have different coefficients. That's why you end up with different pressures associated to those areas. So this is where we get our 1, 1.8, and 2.8 from the ASCE 710. Well, we do the same thing in the 716. It's 10 square feet effective area, and we have basically 0.9, 1.7, 2.3, and 3.2. And this is what you might see normally on a structural drawing where you have, again, the effective wind areas over on one side, and they got the zonal areas. And so what we want to do is look at the 10 square feet again, and we only look at the negative pressure. We don't look at the positive pressure. It really doesn't have any effect on the roofing system's design or certification. So we look at zone 1, zone 2, and zone 3, and I just blew up the pressures to make it a little bit easier. So those are the pressures then we need to make sure that the roof system's been tested to meet or exceed. The other nice thing about this is that they do show that the wind speed is V ultimate, but they also have the VASD. So if you wanted to do the calculations and come down to it. So these are actually ultimate pressures. These are not allowable pressures. So the minimum that would be required is actually multiplying that by 0.6, and those are the pressures that we would then try to make sure that we meet or exceed. This is the zonal, the coefficients again. And the reason I'm showing you both of them is that zone 1 was a 1, and now zone 1 is a 1.7. That's a 70% increase in uplift pressure. So it's a significant change from what was done previously within the documents. So that it's going to make much higher pressures. They also introduced changing the GCPI, which is the internal pressure coefficient. It used to be just enclosed, partially enclosed, and open. Now they have a partially open definition. And the interesting thing about it is that you can see that the enclosed is 1.18, partially enclosed is 0.55, and when you get to partially open, it ends up being back down to 0.18. I believe the thought there is that if there's enough significant openings, that as the wind blows in, it blows out the same way, but it does have a minimal amount of internal pressure that's created. I sort of debate that with people about, because I've dealt with airplane hangars and other large buildings with large openings, and there seems to be a not a proper factor to be used. So I'd be conservative in my opinion and just stay with the 0.55. Now this is a comparison between the 710 and the 716. Building height are 40 feet, exposure C, enclosed, and a risk category 4. And as you can see here for the 710, 120 miles an hour, ASCE 716 to 124. And so the uplift pressures for the field, for instance, is 24 pounds per square foot versus 40 pounds per square foot. Perimeter is 39 pounds per square foot versus 52 pounds per square foot, and the corner is 59 versus 71. For the wind in the field, that is a 60% increase in uplift pressure associated to it. So that can be changing the design considerably, creating a more robust system that may be required to be installed. So just keep that in mind when you're doing again, these documents, making sure that you're using the proper one for the proper area. Now this is the ASCE 722. This one has been adopted into the next version of the building code, which is coming out next year, the 2024. I've actually seen one person use these calculations already in their specifications, so you can actually start using them if you want. But there are some different changes associated to that you got to keep in mind. Now, they're all constantly, these documents are living, so they're constantly changing and modifying them. They've adjusted the calculations again. There's a factor within the calculations called wind directionality. This is to basically allow for that wind is constantly moving. It's not being always a straight line condition. It's always fluctuating backwards and forwards and up and down. So that factor moved from the main calculations, which is that velocity pressure result, down into the zonal areas calculations. And the reason they did that is so their calculations associated to tornadoes would work properly. So now they have a tornado uplift chapter, they have tornado maps associated to that chapter, and they have calculations associated to it also. One thing they did adjust, and I've heard good compliments, but I don't do a lot of steep slopes, is that they changed the roof zones associated to steep slopes. So it should be a little bit easier for someone to work with. Well, with tornadoes, the important thing is first to determine, are you in a tornado region of concern? And this is the tornado prone regions. And you can see that good 2/3 of the United States needs to consider tornado calculations potentially, depending upon a flow chart, and I'll go through that in a moment. This is the winds associated to the tornadoes that we would use in the calculations to determine uplift loads. And the other thing they did is one thing that it's limited to is a risk category 3 or 4 building. So if you're dealing with category 2 type structure, you don't need to do tornado calculations. It's only for risk category 3, 4 type buildings. And calculations are only for up to EF2. So you have EF0, EF1, and EF2 type results that you need to look at. And this is also many maps on square footage, the footprint of the building itself. This particular map is showing 40,000 square foot. So if the building has that kind of footprint, you'd be using this map if it was a risk category 4 type structure. There's a lot of maps. Now, this is the flow chart to determine if you do wind load calculations or tornado load calculations. And you go through this flow chart, it's got all these yeses and nos to it, and then you're able to make a final decision if you should, which one you should use. For instance, this is a hospital in Charlotte, North Carolina. The ASCE 722 says the wind speeds there are 122 miles an hour. The effective planet area I picked again is 40,000 square feet. The tornado winds based upon the maps are 80 miles per hour. It's a risk category 3 or 4 building, yes. In a tornado prone region, yes. Is the VT, which is the 80 miles an hour, greater than 60? Yes. Okay, so far you're looking like you're going to have to do tornado loads, but now you could look at the exposure categories and it adjusts. Exposure B, yes. So if you're doing an urban design in an urban suburban area, you now, following the ASCE 722, you go to the tornado load calculations, not to your standard wind load calculations. But for exposure C or D, you still use the wind load calculations. So that's how it breaks down for how you would use which calculations for what area that you may be dealing with. Of course, if you want to go to extreme, you can use, actually, they have these maps in there that go as far as 10 million year mean return incidents. So that's a significant amount of years to start with, but it also gives you some significantly high winds in their adjustment. By the way, 10 million year mean return means there's a 0.00000001 chance of seeing that wind in 1 year. So it's a very rare event, and you may actually see that. At the same time, to build that structure probably would be very expensive. So that's the other thing, is you can go overboard on engineering, so be careful. Now, one of the other things that has got a bit of confusion on there out in the industry, this is not required by code, but obviously if your building is insured by FM, they want you to follow this kind of stuff. And this is their adjustment or their version of the ASCE 7. What they've done is combine 2 of them together. They're using the ASCE 705 and the 716. They use the calculations of the 705, which is a 100 mean return incident. You use those maps to get the winds. The calculations are based upon the old ASCE 705 version, but instead of using the GCPs of the 05, they're using the GCPs of the 716, which then makes them use the 716 zones, because you now have a zone 1 prime. The results of the calculations come out to 705, or allowable stress, and then they put a safety factor 2 associated to it, as always. So keep in mind, this is not a consensus standard, and this is can get a little complicated. I would suggest, if you want to follow FM in this respect, use the RoofNav website calculator to determine the exact pressures. You're going to find out that they're going to be significantly different than the 710 or the 716. This is a comparison between the 710 and the FM 128, where you have, again, the same configuration we just talked about, but you can see that the pressures that they're showing are significantly higher than you would see for to minimum building code criteria. You can use these, and if it's FM insured, you have to use them. The only thing is to keep in mind that that can be a very expensive installation and costly to the building owner. In this example, the wind loads are 3.25 times higher than the building code. Now, we have the pressures. How do we get the final testing? Well, we follow the FM 4470, the ANSI FM 4474, or the UL 1897. Not a lot of people test associated to this test. It ends up being pretty much close to the same results that we get out of these 2 tests. And these two tests we've been using for decades. So most of the data from manufacturers are actually focused on this. You can list all three in your specification if you want, but just make sure that you don't limit yourself and your designs by just going with the UL 1897. The 4474 is actually a test associated that's listed within the FM 4470, but the 4470 is a group of tests, which includes the Kesterneck test for fasteners, that involves hail tests and a whole bunch of other things that really some are not required by the building code. So if you're just looking at Uplift, this is probably the most important one to make sure that you have listed within your specifications. The test is done by having the manufacturers come in, build a sample, pump positive pressure from underneath it to simulate that negative pressure of the wind being blown across. And then we start off at 30 pounds per square foot, hold it for a minute. We add 15 pounds per square foot, hold it for a minute. We continue that cycle until it actually fails. So keep in mind that a factory mutual 1-90 is actually 90 pounds per square foot. It is not 90 miles an hour. Also note that all the increments are in 15 pounds. So you will not see an Uplift design associated, say, 99 pounds per square foot. There's no rating for that. You'd go up to the next level, which is 105. So it's always going to be in 15 pound per square foot increments. The failure mode that they're looking for adhered systems is the insulation, the membrane separates from the insulation, if the insulation facer delaminates, or if the insulation board breaks. In the example here that you see in the picture, the board broke at this location between the fasteners, and then it started to allow air to build into the system and cause it to peel upward. This is a mechanically fastened system. The failure modes that they're looking here is if the fastener pulls out of the deck or if the membrane ruptures. And it really doesn't rupture. What happens is that as that air builds up underneath it, the plates typically bend or break, and then it tears through the membrane from underneath where the seam's located, and then it turns into this big bubble that's on the table. One fastener fails, it overloads the others, and it just sort of zips across the table. And that's how it fails typically. And that's how we get an idea of what we need to do to increase fastening densities or increase the thickness of the membrane or whatever we're planning to do to get higher uplift pressures. Now those tables are only calibrated to about 300 pounds per square foot. To get anything higher, we have to go and adhere down with some kind of adhesive. And then we use this monolithic pole test where we have this big chain, cranker, and then we actually have a meter here. What we do is we adhere the insulation to the deck in this case, then we adhere the board to it with the metal plate to it, and then we started pulling. This one got up to 817.6 pounds per square foot. In architectural specifications, you might see this wording in there. I believe that Master Spec has this, where it could be either in quality assurance or performance, but basically you're asking for the system to be designed and be tested associated to the uplift pressures of the ASCE 7. But then there's also this little block in the bottom that always seems to be there about FM approved listings. Keep in mind that you should not have that in there. It's just going to, if the building is not FM insured, it's just going to cost more for that installation unless that's already decided by the building owner is acceptable. So keep that in mind that that can be misleading and also add additional costs if the building is not FM insured. Another place you can get listings of membranes and systems is DORA, the Directory of Roof Assemblies. This particular website has the roofing assemblies that are typically used out in the industry, but it also offers wood deck ratings associated to their attachment, be it adhesive or fasteners. So it can be used. It also offers engineered assemblies using a rational analysis. The goal here is to make this site a one-stop shop for Chapter 15. So eventually it'll have included in it is the exterior fire test, interior fire, and the foot traffic test associated to impact resistance of the roof systems. This is a suggested wording that you may want to consider where you're doing basically the same thing again, making sure you test the assembly and it exceeds the pressures. If you want to put a safety factor in there, you can, but not less than 60 pounds per square foot. And then just ask for a number showing that it has been listed within roof nav or DORA. And that's basically the process. We calculate the uplift pressures. We make sure the rated system is rated higher or equal or higher than that, and you've met the building code. Very simple. But if the IBC maps show that I should have a warranty wind coverage of 90 miles per hour, correct? Why is the wind on my warranty less than what is shown on ASCE 7? It states in the performance requirements that the wind speed is 90 miles an hour. Why does my warranty have something less? If the building has been rated for my local wind speed, why doesn't the warranty include the correct wind speed? Well, the first thing to realize is that the building code does not equal any warranties, let alone wind warranties. Building codes do not require a warranty for roof systems or the building itself. So that's one thing you need to, you can take the word warranty or guarantee and put it through the IBC, you will not get one hit. So you're not required to get a warranty from a manufacturer. It's just something nice that we offer people. Other components such as walls, windows, and structures all have to meet these pressures. The engineers got to do them, but they don't carry any kind of wind speed warranty. And warranty wind speeds are not based upon uplift testing. That's a static laboratory test that lasts only 5 to 10 minutes. We use our warranty claim data to actually determine how we want to basically improve the system to be able to qualify for wind warranty. So uplift pressures do not equal wind warranty. So keep that in mind. So if the ASCE 7 is a hot dog, what are warranties? Well, I like to say that the building code is basically hamburger, and going beyond the building code is steak. But when you get to warranties, you're basically looking at the dessert. You have basically a donut to look at. Okay, so it gives you it's nice and sweet, gives you a good feeling in the beginning, and then it gives you a little letdown at the end. So keep in mind that there is no relationship between warranties and the building code. They're completely separate food groups and don't have any kind of relationship to each other. Last few minutes, let's talk about warranty words. The first thing is that you got to understand what warranties are viewed at as a manufacturer, or customers look at it as a statement of responsibility by the manufacturer and the indicator of relative life expectancy of the roof system. In truth, most warranties are used as tools to market and products and limit competition. They are marketing tools to help sell products only. Okay, if you want to take a moment and actually read one, which I suggest strongly, they're basically broken down into two components. The first top area usually defines the system, which can be then what is being warranted, such as the membrane, insulation, fasteners, additional components sold by the manufacturer, and labor. Sometimes you'll just see in some warranties just the membrane being listed. It's a 20-year system warranty, and they define the system as the membrane and nothing else. So keep in mind that's just a glorified material warranty, so they can play with the verbiage a lot within these things. The other one section is the much more interesting one. That's where you run into the detailed assistance of the membrane manufacturer, paying for repairs, maintenance and periodic manufacturer's inspections, and the type of wind and miles per hour for the wind coverage. So let's take a few minutes and look at the coverage versus coverage associated to winds and see how they're not anywhere near the same. When I first started in the business, the company that I was working for basically said that they were offering full gale force wind coverage associated to their roof assemblies. And I thought, well, that's pretty good. And I said, where did you get that term from? And they said, oh, I got it from the Beaufort scale. And I looked at the Beaufort scale and it said, well, it's got moderate gale, fresh gale, strong gale, whole gale, no full gale force winds. So what are you actually using? And they said, well, we're actually using strong gale, but we're using 47 miles an hour is what their limitation was at that time. So that's what everybody was actually pushing for. In fact, some manufacturers are still listing full gale force winds. But down the road we went and we said, hey, we've got better systems, better designs, we got a lot more experience on our belt. What we're going to do is we're going to actually add higher wind speeds, and we're going to publish them this time, right, actually on the warranty. So they went to whole gale storm and 55 miles an hour. So that was when we started actually showing miles per hour on the warranty. And then we went down the road a little more, and they said, well, we can actually offer even a higher wind speed. What we're going to do is storm, and we're going to do 72 miles an hour. So if you've ever wondered where those numbers came from, 55 and 72, it came from the Beaufort scale map. And it was no science, no research. It was just a bunch of guys sitting in a conference room making decisions about a number that they wanted to put on a warranty. Well, back in '88, that was no big deal because those wind speed maps basically were 79 miles an hour. So 72 is close enough for that. Well, as you know, we now have 90 miles an hour maps. We have 120, and we have all sorts all across the map. These are not used for warranties. These numbers are used, or these wind speeds are used in determining uplift pressure so we can meet the building code. These are the building code criteria. This is not warranty criteria. Okay, keep in mind, if we're looking at the 3,000 year mean return incident, that's going to mean that there's a 0.0033 chance, but 120 mile per hour 20-year warranty covers only 0.67 of 1% of that time period. So it's a very expensive design and installation, not really covering anything associated. The other thing is that wind speed warranties are looking at empirical data of actual winds, while these winds that we're looking at versus maps are mathematical assumptions based upon a term mean return incidence. So it's a mathematical assumption. It's not real world kind of data that we're looking at. We're looking at what is our chances of having this type of wind. So keep in mind that we don't warranty chances. We warranty the actual empirical wind results. How is it mentioned on the warranties? No wind speed is covered sometimes. They still reference windstorms, full gale force winds, gale force sometimes is used, and this one manufacturer actually uses gales excluded, which then defaults down to 31 miles an hour. Others use terms like limited wind speed coverage, which I've never got a definition for, capped at 38 miles an hour. Talked to my lawyer about that. He gave me the impression that anytime the wind exceeded 38 miles an hour, that warranty could be voided even if no damage happened. The wind speed coverage was prorated. Was a 10-year, 100 mile per hour warranty. They prorated the wind. So at year 8, they only had 20 mile per hour coverage. And then, of course, you see all the numbers that we print on warranties. Also, where the wind is actually registered at. Ground wind speed is at 33 feet, 10 meters. That's typically what we like to use. No mention within the warranty, which allows the manufacturer to pick where that wind is. And sometimes you'll actually see it being referenced as rooftop wind speed. And where that becomes a factor is if you're dealing with a high roof, say the building owner has a 300-foot high building and you want a 100 mile per hour warranty. Well, that actually, if he gets to the rooftop, it's going to be 55 miles per hour at ground. Well, if you take a 100 mile per hour at ground wind speed, it's actually 180 mile per hour at rooftop. So you get a little bit more coverage when you're dealing with ground wind speed warranties than you would. Now, again, this is solely if you're dealing with high-rise types buildings. And then in the warranty section, this is always very important to realize that you want to make sure that you have the correct words in the correct area. The warranty section is where you're looking for a manufacturer to supply the warranty. It's not in the performance. Again, that's building code. That has nothing to do with warranties. And so this is the donut section. So you want to make sure that you list the wind speed that you're looking for from that manufacturer and where it is actually measured at, so you're getting manufacturer to manufacturer offering as close to the same donut as possible. Don't rely upon the performance. So this is the last couple of slides here where, have the building owner read the fine print, request warranty samples, really study the duration versus the coverage. I've seen shorter warranties sometimes offer better coverage, and get clarification in writing. So that's basically the design process. Calculate the pressures, test the system to meet or exceed those pressures, and then you overlay that with the potential cost increases associated to the warranties. And there are significant costs that can be found by just looking for a warranty. This is an example. Now keep in mind all the designs that I'm pointing out here are going to meet the uplift pressures. This was some figures that were given to me for a 20-year warranty. The building would cost about $100,000 for the roof system. At 55 mile per hour, there's no increased cost, but for 90 mile an hour, when you're looking at the additional components, materials, and labor, that can be a 10% increase overall. And then if you're going from 55 to 120 miles an hour, that's a 20% increase in overall cost. So keep that in mind, that the building owner should be making the decision. Does he want to spend an extra 20% on his roofing system just to get a 120 mile per hour warranty? It should be his choice. It's not, you should not relate that to, again, the ASCE 7, because there's no connection between the two. It's just a cost impact. And with that, I have probably a couple of seconds here that can be the offer and answer to any questions. Few roofs have an anemometer. Where shall I measure the roof wind speed? Airport, that is 20 miles away. Typically, we use weather stations or the airport, but we also go back 6 months. And the reason we do that is because the building owner a lot of times doesn't really realize he's got a problem with his roof, except down, he doesn't know until he hears a flapping, and that could be sometime between around 6 months. So we do an in-depth review to make sure that if we have a problem with our warranty, we're going to basically cover it. I can't speak for other manufacturers. I can only speak for myself in that respect. Anything else? Okay, there is one other question that I have here, real quick. Why are we calculating for tornadoes and exposure D and not the other areas associated to that? Well, yes, the reason for that is because they're looking at population density. They're figuring that in exposure C and D, you won't have as a high a population, and also the winds, especially along D, especially along the coast, have already been calculated associated to the hurricanes and tornadoes that can be generated. So they feel that that's basically what they need to do. So another question here real quick. You mentioned allowable and ultimate. What does service and nominal mean? They basically are redefining what allowable actually is. So allowable, service, and nominal are the same. And with that, I want to thank you very much for participating, and have a great day. Thank you.